Hello, my name is Kyriakos Destounis, and today I'm going to give you a brief presentation of my recent work for the last couple of years regarding the inspiral and the ring-down stage and how we can use those to test the strong field gravity regime. So let's talk about black hole binaries because this is the main state of the art, which is gravitational waves. And I will briefly go through this very nice inspiral signal that has been created with numerical relativity and has been reconstructed from the first gravitational wave detection called GW150914. So what we see here is an almost equal mass binary that starts with the states called inspiral, where the astrophysically captured compact objects, in this case black holes, are spinning around a common center of mass. Then they emit gravitational radiation, and this makes the inspiral going closer and closer. The frequency increases because we are losing energy and angular momentum. And finally, on the peak of the amplitude, the merger happens, which is the second stage where the two objects collide. And this is a very highly dynamical and strong field regime. And finally, we have the so-called ring-down stage, where the perturbations, the final perturbations of the remnant are decaying exponentially, and the object emits gravitational, the excess gravitational radiation until it relaxes into a stable state. Now, what we have now is three ground-based detectors, LIGO, Virgo, and Kaga, the laser interferometer gravitational wave observatory, Virgo, and the Kamioka gravitational wave detector. This collaboration is now at its third observational run, so we have increased the sensitivity a lot since the first gravitational wave detection, and we have at least 90 confirmed detections so far from observations, which is a really huge number for us to do data analysis and test the strong gravity regime, which is elusive at the moment. Now, these detectors, because they are on the ground, they are working at the kilohertz frequency range, so they have sensitivity around this kilohertz, and just for time scales, this inspiral takes fractions of a second and has a very small strain, 10 to the minus 21. So it's very hard to detect. Now, let's talk about the first part of my recent interests, which is the inspiral stage. So, how to motivate this? We have seen, or I discussed a little bit briefly about the part where we have some equal mass, an equal mass binary where the two objects are very close to each other. This regime has a mass ratio close to 1, where the mass ratio is the ratio of the two components, the masses of the two components of the binary, and small separation. This means that we're in a highly non-linear dynamical regime, and we can only use tools of numerical relativity to probe such regions and recreate the final stages, the final revolutions of an inspiral before the merger and the merger itself. But if we increase the mass ratio, and in this case, the mass ratio is the primary over, let's say, a secondary object, which is much smaller, so mass ratio increases, the separation becomes irrelevant, and we can use perturbation theory because this small compact object now perturbs the space-time geometry of the primary compact object, and we can use perturbation theory techniques and gravitational self-force in particular. Now that is the best way of making gravitational wave templates in this case, in the extreme mass ratio regime. And this gives rise to extreme mass ratio inspirals, where we have a primary supermassive black hole and a secondary stellar mass compact object. These extreme mass ratio inspirals, these EMRIs as well call them, originate in dense stellar clusters and galactic cores. And the mass ratio that they allow span from 10 to the minus 7 to 10 to the minus 4. Here, the mass ratio is the secondary over the primary. They generate, because of their nature, 10 to the minus 4 to 10 to the minus 1 hertz. So completely different frequency regime from the one that ground-based detectors are currently probing. So we cannot see EMRIs with our detectors now. These ones perform 10 to the 5 revolutions, or at least 10 to the 5 revolutions around that number in the strong field regime, which means they will give us amazing signal to noise ratio and rich way for phenomenology. Now, how we can probe these ones with space-based detectors, which have been funded already and constructed at the moment as we speak, and these extreme mass ratio inspirals are prime targets of these detectors. One of them is the laser interferometer space antenna, or as we call it, LISA. These ones, these extreme mass ratio spirals, will be visible for years in this frequency band of LISA, and therefore we are currently highly expect them to appear when the detectors are up and running. Now, how do we model an extreme mass ratio in spiral at the orbital level? At short time scale evolution, because the secondary is much smaller than the primary, we can assume geodesics. For some cycles, we can assume a geodesic equation holds. So let's choose a stationary and axisymmetric spacetime, the most general we can choose with this particular line element. And then we have the geodesic equation. Now, from this line element, the Lagrangian appears, and from the Euler Lagrangian equations, we can calculate the equations of motion of the secondary, of assuming there is a test particle, and instantly we can see that we have two conserved quantities. From stationarity, we have the conservation of energy per unit mass. From axisymmetry, we have the conservation of the z component of the angular momentum, and also we have the conservation of the rest mass of the secondary particle. So we have 4 degrees of freedom in our space-time metric, and 3 constants of motion. If we have an extra one, then we have a very nice deterministic evolution and no chaotic phenomena appear. In the case of a Kerr black hole, for example, we have the Carter constant, which separates radial and polar motion, and it leads to integrability. So whenever we don't have a fourth constant of motion, being Carter or Carter-like, or any other higher order rank killing tensor, then we will say that we have non-integrability and chaotic phenomena or full-blown chaos may appear. Now, at the long time scale evolution, an EMRI, of course, emits gravitational waves. So we have to take into account the so-called radiation reaction that occurs. And there are 2 ways of doing that with perturbation theory. The first one is assume an adiabatic approximation where the change in the momenta, the energy and the angular momentum, is small over a single orbit. And this way we can approximate the fluxes with post-Newtonian formulae. This is where the Kladsky comes. And then we can approximate the gravitational wave emission with a quadruple formula or higher order multiples. And this is up to us. Now, this leads to an evolution where in short time scales the orbit neglects radiated back reaction, and at a long time scale the inspiral behaves like a flow through successive geodesics. And this is one of the techniques that have been used primarily for the last 20 years. It's a very old one, but very, very well known and used, and it matches very well with what we see from the second technique, which is basically to solve directly the source, the Kolsky equation. So the Kolsky equation with a source, where the source is the secondary particle, and then calculate the Weil scalar. From the Weil scalar, find the fluxes of energy and angular momentum, plug them into our inspiral and the geodesic equations, and it becomes an inspiral. This way we find the fluxes as I explained, and then we can have an inspiral. So we have 2 techniques. The second one is the most accurate one, but both 1 and 2 match, at least for Kerr EMRIs, up to 95%. So the first method is a really good one. Okay, now Let's talk about resonances, because this is going to be one of the part of the talk here. Resonances are just periodic orbits, really simple. And in extreme mass ratio spirals, we expect to see and experience a lot of transient resonances, in contrast to what happens in the LIGO band in equal mass binaries, because they evolve so fast that they cross through these resonances extremely fast that we don't even see them. So resonances, as I said, are they exist. They will exist in EMRIs, and they may ruin or at least affect parameter estimation by some percentage. But having a Carter constant, or in general having a perfectly vacuum Kerr spacetime, is really, really is really hard. Is a really hard thing to do, to have a Carter constant. So if we consider a weak perturbation to Kerr, any generic perturbation to Kerr that is weak enough, as we write here in this equation, so we have the Hamiltonian of Kerr plus a perturbation with a scale epsilon that is much smaller than 1, then we have two theorems that tells us what happens around resonances, so how the structure of the phase space changes. The first one, the KAM or Kolmogorov-Arnold-Moser theorem, tells us that if the perturbation is non-integrable, then the dynamics just smoothly depart from that of the Hamiltonian of Kerr if we are away from resonances. And there's a way to quantify that. The Poincaré-Birkhoff theorem, on the other hand, tells us that close to resonances, we have the formation of Birkhoff chains. So what we see here is a surface of section where an orbit intersects as it revolves around the primary object. And when we are away from resonances, as you see, we form these KM curves, these continuous circles around the central point. And when we are close to resonances, we form these nested islands that do not surround the central fixed point of the phase space, but the periodic, stable, resonant points. Also, what we have, as we expect, is chaos. So we have these unstable points, these open circles. These are stable periodic points, which give rise to chaotic orbits that form thin layers around the island, outside of the island. What's the most interesting thing that you should keep from here is that the orbits share the same rational ratio, which is called the rotation number, in the island. So this rotation number, the rational ratio of these two frequencies, the periapsis to the apoapsis frequency, omega r, and the theta plus to theta minus longitudinal oscillations of the orbit, it remains constant when an orbit crosses through an island. And this is very important here to remember. Why? Simply because if we evolve an inspiral with some mass ratio that makes it an extreme mass ratio inspiral, and we keep track of the rotation number with particular techniques, then we see that as it evolves with time, and the time here is months because we have longer time scales, as I said, of evolution, at some point drops into a flat line, where we call it a plateau, and then goes away. This plateau designates the constancy of the rotation number, as we discussed before. So here we have chosen initial conditions so that we cross through an island, and the crossing is very obvious at the orbital level. At the gravitational wave level, we form a very beautiful figure here, which we call the gravitational wave glitch. It's astrophysically relevant because if we break the integrability properties, if there's an astrophysical environment, if there's a modification of gravity, and so on and so forth, this fourth constant of motion is really hard to keep. Therefore, these glitches are expected to appear. By the way, even the average crossing time through an island changes. Before in Kerr, like the studies have shown that the resonance may last for some cycles, some dozens of cycles, but here we have at least 250 cycles in perfect resonance without taking into account the pre and post resonant effects. Now, these extreme mass ratio inspirals that are non-integrable, there's a huge class of them. The previous one was a bumpy, deformed spacetime that we deformed by ourselves, but this one is for a boson star. And you see how many beautiful things you can see here. We see simultaneous glitches. So we can distinguish between different phenomena if we have different compact objects that are supermassive in the center and are non-integrable. This is a particular case for rotating boson stars from a recent study. Now, let's put these extreme mass ratio inspirals into an astrophysical environment. Why we want to do that? Simply because the rotation curve of a galaxy does not uh, uh, the observed rotational curve of a galaxy does not match the rotation curves that are predicted by Keplerian dynamics. And why is that? Because something is missing. And what is missing is more mass to keep the rotational curve constant in far distances in the galactic spiral. So if we have a spiral galaxy, let's say we have a galactic bulge somewhere here in the center, we have seen that we have supermassive black holes. So the supermassive black holes are hosted in the center of galaxies. We have the galactic disk with some luminous matter, planets, solar systems, and so on and so forth, stars, dust. And then to make this make sense observationally, we have to add some matter. We cannot see this matter. It's non-luminous, like the one of the galaxy. Therefore, we call it a dark matter. And in this particular case, a galactic dark matter halo, which is large enough to keep the rotational curve flat and make this system observationally and theoretically viable. Now, up to this point, nobody has found a fully relativistic configuration that described the previous figure. The plethora or the majority of the literature deals with the galactic dark matter halo as an addition of a post-Newtonian potential. Here, I'm going to use the Einstein cluster construction, which assumes an average stress energy tensor of all possible spherical geodesics up to the radius that defines the scale of a dark matter halo. So essentially, we take an average stress energy tensor, which corresponds to an averaged, the averaged momenta of the particles. This is the particle density, the test particle density, and these are their masses. And this can correspond to an energy momentum tensor that is anisotropic, is diagonal. It has an energy density, which we can choose to be of a dark matter halo profile that comes from observations and galactic dynamic simulations. It has a zero radial pressure and tangential pressure. Now, let's assume a spherical symmetric line element of this form. You see now that the mass has to be a variable, a variable of r. So the mass depends on the radius now, and we choose a matter profile. In this case, a dark matter profile, which is called the Hernquist distribution. Hernquist distribution is very good to describe galactic bulges and elliptical galaxies. Therefore, in the Hernquist profile, we add a black hole here. So the mass that we're going to input in this line element has a black hole mass plus something that comes from the energy density of the dark matter distribution that we have chosen times this very common factor that we need in order to have the black hole in the center of this halo. Now, by solving the resulting field equations and taking into account the BIK identities, we can find the energy density and the pressure. And the energy density has this form. You see that two new constants appear, which were appearing even before, which besides the mass of the black hole, we have the mass of the dark matter of the halo and the length scale of the halo, A0. Now, A, which we had in the line element before, is nothing but this nice known spatial factor times a much more intricate one with square roots and this C parameter, which is just dependent on the black hole and the dark matter profile parameters. Now, we have an event horizon that lies at r equals 2m dh. The spacetime is asymptotically flat. When we go close to the event horizon, this factor here becomes a redshift factor, so 1 minus 2m over a naught. We have to remember that because it will appear later. And to mimic galaxy observations, the compactness of the halo, as we call it, m over a0, has to be smaller than 10 to the minus 4. There's a scale hierarchy here. The mass of the black hole has to be much smaller than the mass of the dark matter halo, and in turn, the dark matter halo mass has to be much smaller than its length scale. So the halo redshifts the orbital dynamics of particles at leading order in m over a naught in the compactness. And of course, this is an exact metric, but choosing different matter profiles is straightforward. But the solutions that we have found so far in this literature, for example, are all numerical. Okay, so let's evolve an EMRI in this astrophysical setup, this configuration, and see if we have we can detect an astrophysical environment. So what we have done here in this figure is that we calculated fluxes of an EMRI that evolves in an astrophysical environment, the dark matter halo of the Hernquist, over the flux of energy of a vacuum of a circular equatorial inspiral. And we use the Kolsky-based waveforms to Kolsky-based techniques to find these fluxes. And we see that they deviate, of course, from one to another by at almost 2% as we go to the strong field regime, which is important because the halo properties affect the gravitational wave emission even at the adiabatic level, without even taking the conservative effects into account. The difference with vacuum fluxes grows with the dark matter distribution mass, m, and a dephasing appears between the vacuum and non-vacuum evolution of the EMRI of 500 radians, so 500 revolutions. This is more than observable level for space-based detectors. Therefore, the perturbative, and later on, besides this work, we have also introduced in the literature a fully relativistic perturbative framework to treat non-vacuum EMRIs with axial and polar fluxes. I state that here because here we have only used the axial sector, which is much easier to treat with the Kolsky-based waveforms. Here it's not the Kolsky exactly, it's Reggie-Wheeler, for example. Anyway, now let's go to the ring down really quick and see that the ring down is the final stage, as we discussed before, of the remnant of a merger. And this ring down apparently can be characterized by the so-called quasinormal modes, which are not normal modes as we know, that vibrate forever, but are quasi-normal because besides a real part which corresponds to the vibrational frequency, they have an imaginary part that brings some decay into the system, as we see here, exponential. And this omega I is it's called the decay timescale, or is associated to the decay timescale of this ring down in the time domain. Now, assuming that we know, again, how to treat perturbation theory in this case, we have no sources, we just have this equation, which is a wave equation essentially with an effective potential, which effective potential has this form. L here is the angular quantum number, and GTT is a metric tensor component. Here we will assume for simplicity spherical symmetry. Now, again, let's go to the ring down stage, calculate these quasi-normal modes for a black hole in the Hernquist profile, surrounded by this astrophysical environment. The wave equation changed slightly, only the actual effective potential changes, and this is because the mass now depends on R, and we have also derivatives of the mass function. And as we can see, both real and imaginary parts decrease with the compactness, and this is where the redshift comes. And there's a minimal dependence on the mass. We have chosen masses of 20 black 20 MB8 and 10 to the 3 MB8. So the central black hole can be either stellar mass or supermassive, and we still have the same imaginary parts and real parts. So the same trajectory in the complex plane of the quasi-normal modes for even the first and second overtone. Now, let's see this figure a little bit. We have plotted here the real part and the imaginary parts of an L equals 2 and different overtones n of quasi-normal, the fundamental of a quasi-normal mode in a galactic dark matter halo. That's why we have this M and A naught here, and we plot it with respect to the compactness. And we do a fit on the modes that we find. We choose, of course, different masses as before, and we see that the fit is perfect. So what does this fit tell us? First, it tells us that the quasi-normal modes have a clear light ring interpretation, because when we take this ratio of the quasi-normal modes inside the dark matter halo and the quasi-normal modes in vacuum, then we have, again, the redshift factor appearing 1 minus m over a naught. Therefore, we have a redshift of QNMs when we introduce a galactic dark matter halo in our system. And this makes sense because of dynamical friction. Perturbations interact with more matter than they were supposed to when they are in vacuum. Now, the final thing that I want to discuss is this new topic of spectral instability of quasi-normal modes, but I call it new because we just applied it in black hole physics, but there are papers even going back to the 90s by Hans-Peter Noller, for example, when he tried to discretize the effective potential of a Schwarzschild black hole in an attempt to form a complete basis of quasi-normal modes. He fixed this issue, the completeness of the set of quasi-normal modes, but in return, he got a completely different spectrum. That's why we call it a spectral instability. So the continuous line here, the continuous potential, has quasi-normal modes that are in asterisks, and you see that they are going up really quick. But when he was introducing more and more steps, he was getting branches that were going more and more down, which means that the spectrum itself has a tendency to change dramatically when we introduce very small perturbations, especially like the more steps he introduced, the more this line was going down, so further away from their initial state, especially the overtones. And look at them. Anyway, so this is where the pseudospectrum kicked in, which is a mathematical notion, a mathematical tool that has been used in many, many different other fields of physics, engineering, chemistry, and so on and so forth. But for the first time in 2021, by Jaramillo and other collaborators, it appeared in black hole physics. And it's beautiful because the pseudospectrum can tell us if we have a spectral instability without doing perturbations onto a potential. Now, just as a start, let's see how a spectral stability and spectral instability looks in a very simplified model where we have the Poisson-Teller potential instead of the Schwarzschild potential. Okay. Now, spectral stability means that, first of all, we have normal modes. Okay. Why we have normal modes? Because to make a system spectrally stable, like the black hole one, we need to kill dissipation. We need to take out dissipation out of the equation. Why? Because dissipation makes the operator that describes the whole wave equation non-self-adjoint or non-normal. And this means that we do not have an underlying spectral theorem. But in the case of spectrally stable spectra here, like normal modes, we have a spectral theorem, and it tells us exactly how these pseudospectrum lines will go. The normal mode will appear, and concentric circles of scale epsilon, let's say, will appear, and this is the scale epsilon here. in a logarithmic scale, and here as well. And this means that the system is spectrally stable in a sense that if we add the perturbation of order 10 to the first, we will go as far away as here, which is of order 1 migration of the QNMs, of the normal modes in this case. So whenever we see concentric circles of radius epsilon, then we have spectral stability. So the pseudospectrum can give us information not only about the spectral stability, but the overall migration of the quasinormal modes, the topographic map, let's say, of quasinormal mode migration. And here, when we have an actual black hole-like system with the positive potential, and we have dissipation on the left and right hand side, which means dissipation at the event horizon, the would-be event horizon. Here again, it's a positive potential, and dissipation on at infinity. So outgoing waves at infinity, ingoing at the event horizon. Then we see that the spectral instability appears through the pseudospectrum contour lines, these white lines that correspond to different scales here in the color map. So they open up as Noller has found when he was perturbing his potential. And for example, if we choose 10 to the minus 10 perturbation, we're somewhere here. So from this overtone and on, all the rest of the modes can migrate all over the place, and the maximum migration can be down to here. So they go from the lines and up. So, but they usually have the tendency to, most of the overtones to come on top of the lines. And we can see that in the pseudospectrum of actual black holes. This here on the left, for example, is for Schwarzschild black holes, and these quasi-normal modes, the red dots, are the gravitational quasi-normal modes. We see that if we do some specific perturbations, which in their paper they call deterministic, where they add a cosine, a sinusoid perturbation of frequency k to the effective potential of Schwarzschild, of the axial modes of Schwarzschild, and they use different norms of the potential 10 to the minus 8 and different frequencies. They see that as they increase the frequency of the perturbation, these branches open up, these red points here, for example, and they go and match as good as they can match these pseudospectral contour lines. So a perturbation of the potential is good enough to make a spectral instability, to produce spectral instability, even when the perturbation is very small, 10 to the minus 8, 10 to the minus 4, with some high frequency. The same thing happens in Rise and Nordstrom black holes here on the right, which we have studied. Again, these are the gravito-electric modes because they are coupled. Gravity and the metric perturbations here that we have done lead to gravity and electromagnetic modes that are coupled. But in any case, we can still see spectral instability. So we conclude here that the pseudospectrum can tell us what can happen to the overtones and to the fundamental mode when we perturb the potential with some perturbing factor. But the pseudospectrum is oblivious to the perturbation. We do not have to choose. It tells us what's the maximal quasi-normal mode migration blindly, without choosing any perturbation, without adding anything by hand. And this is obvious here. Now we have done the same with exotic compact objects, which tend to have non-linear instability. So they become non-linearly unstable when we put higher order perturbations on them. And this has been seen in numerical relativity simulations and proven analytically. And here the pseudospectrum, very surprisingly, tells us that for an exotic compact object, which has a perfectly reflecting surface a little bit outside the event horizon, so we have no dissipation at the event horizon because it doesn't exist, we have full reflection, leads to these modes that are almost at the real axis, so they have a very small imaginary part, and they just need a tiny push to cross over to the unstable part of the complex plane, where actual unstable quasi-normal modes appear. Now, the pseudospectrum at the linear order, the pseudospectrum tells us that these contour lines cross over. So a small perturbation can really turn the system unstable. So the spectral instability here of quasi-normal modes entails at the linear order that nonlinear effects should render this whole compact object unstable. And here we see it at the linear order, which is a really beautiful and insightful result. Finally, let's add astrophysical environments as perturbers. So let's choose a thin cell, which creates a tiny bump here. We will choose how large and wide it is, if it's a post-stellar or Gaussian. We have done both, of course. And this is the main peak, the big one of L equals to axial perturbation. So for the Reggie-Wheeler effective potential. Now, let's add this perturbation and see what happened to the quasi-normal modes. So here we see the original mode, and overtones take over or overtake the original fundamental mode as the bump goes further. Here, this is not to scale, but we increase the distance between the bump and the light ring peak. And we see that overtones first overtake until we have a huge jump in the new fundamental mode, which means destabilization of even the fundamental mode, which we couldn't see clearly when we were doing this cosine perturbations. But here is very, very obvious. And to finalize, this is the trajectory that the fundamental mode undergoes. It spins around as we saw the spiral, goes to peak, and then it starts going down. Overtones overtake this one because they have smaller imaginary parts. As we go more down, other overtones overtake until we have a huge jump to some smaller imaginary part that comes from a very much higher overtone. Essentially what happens is this trapping surface between the light ring bump, the light ring peak, and the small bump creates trapped modes, which lead to these echoes, as we have seen them in the literature in the time domain, and to these very, very long-lived quasi-normal modes with extremely small imaginary parts. And here, if you see the difference between the perturbed and the unperturbed quasi-normal mode grows exponentially, the real and the imaginary part, and they reach the levels close to 10 to the minus 1, even though we introduced the perturbation of 10 to the minus 6. So this is, again, a spectral instability. To finalize, from the Inspiral studies, we have seen that black hole perturbation theory provides a very nice framework to treat EMRIs and gravitational wave generation. We expect thousands of EMRIs to be detected by LISA and other space detectors. And first, we have seen that non-integrability is imprinted in EMRI gravitational waveforms in the form of these glitches. We have also seen that astrophysical environments around EMRIs can impact gravitational wave generation and propagation to observable levels. And what we need to do is model these gravitational waves from extreme acceleration spirals in order to understand modifications of gravity, environmental effects, quantum effects, and so on and so forth. At the ring-down stage, we saw that again, black hole perturbation theory is the perfect tool to analyze ring-down signals. Astrophysical environments around black holes redshift quasi-normal modes, as a lot of studies have seen. Black hole spectroscopy relies on the spectral stability of quasi-normal modes, which is a program that actually tries to fit QNMs on ring-down signals from gravitational wave data. And if spectral instability also appear, they should be taken into account in the black hole spectroscopy program, because or else we will have problems. We will do wrong fitting. Now, the pseudospectrum, as we have seen, can assess to which extent quasi-normal modes exhibit such spectral instabilities, and therefore quasi-normal mode spectral instabilities may limit the abilities of black hole spectroscopy. And that is all. Thank you very much.